Hello everyone. So we will discuss how using a template I will show you how this truck factor method and the vehicle damage factor method is used to determine the equivalent standard axle loads. So what you see here is the um, uh, template in which you actually mark the axle load data that is being collected. You can see here there is the serial number and the number of axles, so you can read the serial number part. This is a traffic which comprises of 2 axle truck, 3 axle and 4 axle and 5 axle. I'll show you what are the different classes. So for the different classes or the vehicle types, you measure the wheel loads. Okay, so in this here a portable small weigh pad was used, wherein you will note the wheel loads essentially and not the axle load as such. So you can see here that the wheel load is noted here as 1.7 and for the rear wheel it is noted as 3. Okay, likewise in the case of you have like commercial vehicles, bus, etc. And when you go to a 3 axle, you see that there is a front axle and in the rear you have a tandem axle. So in the tandem axle you note the what is the load on the first wheel of the front axle and the second wheel of the front axle and so on. So likewise this data is collected. Now once collecting the data, you can see that in this Excel sheet I have marked it as different pages, as one is the 2 axle truck, the other is named as 3 axle truck, 4 axle truck, then 5 axle truck and so on. Okay. So if you say there is a 2 axle truck, this is an example of the 2 axle truck that you are considering. So see, there is a front axle with a single axle single wheel and a rear axle with a single axle dual wheel. So this class is categorized as a 2 axle truck in the study. And then moving on to the next one, which is a 3 axle truck. As you see here in this picture, there is a front axle with single axle single wheel, and at the rear there is a tandem axle, but for convenience it is written as 2 axles. So altogether this is 1, 2 and 3. Okay, so there are 3 axles, so this is why this class is named as a 3 axle truck. And then you have a 4 axle truck here. You see that at the front there is a single axle single wheel assembly, and then you have a single axle dual wheel assembly, and then there is a tandem axle which is counted as 3 and 4. So there are 2 axles, so altogether there are 4 axles. Okay, so this class of vehicle is classified as a 4 axle truck. And then comes the 5 axle truck. You see here that there is a front axle which is single axle single wheel, and there is a single axle dual wheel which is your axle number 2, and there is a tridem axle. Okay, each axle has dual wheels, so this is a tridem axle, so which is counted as like 1, 2 and 3, or I say 3, 4, 5. So altogether there are 5 axles. So this class of truck is named as 5 axle for convenience. Okay, so accordingly I have all these Excel sheets here. So let us see how the data is tabulated in this table. So this is the original data as you see here. Okay, so this is the data in which the single axle single wheels of all those loads are presented. So this is the wheel load in tons as 1.65, 1.7 and so on for each of the vehicles, and it is multiplied by 2 to get the axle load. So in the single axle single loads you have then in tons, it is then converted into kilonewton. So you see that this is the axle load data that you have collected for the front axle of this 2 axle truck. Okay, and similarly on the rear axle you have a single axle dual wheel. So for all the trucks that you have surveyed, you see that the wheel loads are 2.95, 2.75 and so on, which is multiplied by 2 get the axle load, which is then converted to kilonewton. So you get the axle loads on the rear. So you have, like in this case, there are a total of 208 vehicles were surveyed, and of all the 208 vehicles we have measured what is the front axle load and the rear axle load. Okay, so you have 2 axles. Now let's see how the equivalent standard axle loads are calculated. So this is a 2-axle vehicle as you see here. Now the front axle as I said is a single axle with single wheels on either side. So for that the equivalency factor is 65 kilonewton, or I mean not the equivalency factor, the standard axle load is taken as 65 kilonewton, and the equivalency factor can be computed as the axle load divided by 65 raised to 4, as you have seen it is written on this. Let me just zoom it a little bit. Okay, so this data has to be, the data that you have has to be now grouped into different axle groups. Okay, now as per IRC, it suggests that for single axle dual wheels you can have a bin size of 10 kilonewton. So the single axle single wheel load also, it is not mentioned in the code, but we have taken a bin size of 10 kilonewton. So this is the class interval you see here. This is 0 to 10 is the first class, 10 to 20, 20 to 30, 30 to 40 and so on. So up to 80 to 90 is, you have divided it into 9 class intervals based on what is the minimum and the maximum values that comes in this data. Okay. Now this gives you the mid value of each bin. So 0 to 10 the mid value is 5, and 10 to 20 the mid value is 15 kilonewton and so on. Now you do you find what is the frequency of each one of these each of these load groups. So from the data, as you see here, this is the data. So from this data you have counted how many number falls in the 0 to 10 category, how many axle loads are in the 10 to 20 kilonewton category and so on. So this is the number of axles, or you call it as a frequency table. Okay, so this gives you the frequency of distribution of the load. You can say what is the percentage of each one of these loads in this category. You see that most of your 29.8% of the load comes in the 30 to 40 kilonewton category in this group. So this is just for the understanding of how the load is distributed. This column is written here, and also a cumulative percentage is calculated, so that you can just see that whether all the vehicles are included in the analysis. So just for the sake of convenience only, we find the cumulative percentage, or if you want to draw a cumulative frequency chart, you can use this information. Okay, so moving on. Next you have to get the equivalency factor. So as I said, you consider the mid value of each load group to find the equivalency factor. So for the first class from 0 to 10, your 5 is your mid load group. Now the equivalency factor is 5 divided by 65 raised to 4, because 65 is the standard axle, okay, axle load. So for each class, so for the next class 15 is the mid value. So the 15 divided by 65 raised to 4 will give you the equivalency factor. Likewise, for each load group you have determined what is the equivalency factors. Now you have to convert the number of number of axles in each of these groups to the equivalent standard axle. So how do you do that? You multiply the number of axles in that group with the equivalency factor, so that you will get what is the total equivalent standard axles in that load group. So as you see here, in the first category 0 to 10 kilonewton, you had only one axle. So that one axle multiplied by 0.000035 was the equivalency factor. You got the total number of equivalent standard axles. Likewise, for each load group, you have the equivalency factors and the frequency in that load group, or the number of axles in that load group. You multiply to get the total equivalent standard axles. You add all them together, you will get what is the equivalent standard axles that is formed from the all the front axles of this 208 vehicles that you have surveyed. Okay, and the percentage damaging effect of each one of them can be computed, because this equivalent standard axles essentially tells you how damaging this axle was. So it contributes to around 70.85, of which you can see that 14% or 32% is due to the vehicles which comes with a load range of 60 to 70 kilonewton and so on. So this information you can get from this table. Okay, so for all the 208 vehicles, you have found out what is the equivalent standard axles due to the front axle. Okay, now moving on to the rear axle, which is a single axle dual wheel. Now what is the standard axle for that? The standard axle load is 80 kilonewton, right? So the load in the mid value of that load group by 80 raised to 4 will give you the equivalency factor. So again you can see that the load is grouped into 10 kilonewton groups. So you can see, or ranges, you can see that 0 to 10, 10 to 20, 20 to 30 and so on. It is divided into class groups and the mid value is taken as the load for that particular class group. The number of axles or the frequency is estimated from the data, as I have already shown here. This is the data there. And then you see what is, and the percentage of each category and its cumulative percentage of all also is marked here. Now you get the equivalency factor. As I said, the mid value of the axle, say for example, suppose the year 50 to 60 is the load range. See, let me just explain this called a row. So 50 to 60 is the load range. So 55 is the mid value. So your equivalency factor will be 55 by 80 raised to 4. Now that is equivalency factor multiplied with the number of axles in that group, which is 15, which will give you the total equivalent standard axles of that load group. Likewise, you find out the equivalent standard axles of all the rear axles of this particular class of vehicle, of all the 208 vehicles that you have surveyed. So you get a sum which is 479. So the damaging effect that is caused by the rear axles is 479. Now you have counted 416 axles because there were 288 front axles and 208 rear axles. So the total number of vehicles is 208. The total damaging effect is due to the front axle plus that due to the rear axle, which comes to around 550. Now you can find the truck factor for this 2-axle truck as given by the total damaging effect, which is 550, divided by the number of trucks that you have considered, which is 208. Suppose you want to find what is the axle equivalency factor, you can divide this total damaging effect divided by the number of axles. Okay, so this 1.322 is essentially something like of an axle equivalency factor, but what you need is a truck factor, which is the total equivalent single axle loads from the front and the back put together and divided by the number of vehicles that are counted, so which is 2.644. So for the 2-axle trucks in the study, it is 2.644. Now let's move on to the 3-axle truck. So as you see here, in the 3-axle truck, there is the front single axle single wheel and the rear, which is a tandem axle. Okay, so the data that is put here, let me just show you how the tandem axle data is noted here. See, in the case of the tandem axle, you can see this columns here. See, the weight on the first axle, the one wheel of the first axle is noted, and the weight on the one wheel on the second axle. So you have tandem axle, 2 axles. On each axle you note the weight on one wheel, multiplied with 2 will give you the weight on that particular axle. Okay, so you got the axle load on one axle of the tandem wheel and the other axle of the tandem wheel, and it is summed together to get the total tandem axle load. So this is how you collect the data from the field and you sum it up together to get the axle load. So you can see that 216 kilonewton is the axle load of the first vehicle, 224 is the tandem axle load of the second vehicle, and so on. Okay, so you have this information. So again, this truck has 2 classes of axles. The first is the front axle, which is a single axle single wheel with the standard load of 65 kilonewton, so that the equivalency factor can be calculated as axle load by 65 raised to 4, whereas in the rear you have the tandem axle where the equivalency factor is 148. I hope you remember from the IRC code we have mentioned. So for the tandem axle, you can get the equivalency factor as axle load divided by 148 raised to 4. So again, the frequency is put into the load groups. We have started from 30 to 100 kilonewton, and in between there could be some load ranges where there are no vehicles, so which is omitted from this table. So you have to just take it in 10 kilonewton intervals, so 30 to 40, 40 to 50 and so on. The mid values are written here, and then the number of axles or the frequency is noted. Equivalency factor for each of those mid values of load is noted, and then multiplied with the frequency will give you the total number of standard axles. So the front axles will give you a total damaging effect of 224. Likewise, for the tandem axle, you see that the load range is taken in the range of 20 kilonewton, because 50 to 70, since it is a tandem axle, you can take a larger range of 20 kilonewton each. So 50 to 70, 70 to 90 and so on is the load classes that you have taken. And then the mid value, the frequency, then I have just noted the percentage of frequency in each category, and the cumulative frequency is also noted here. Then the equivalency factors are computed using the equation, and each equivalency factor multiplied with the corresponding mid value will give corresponding frequency will give you the total equivalent standard axles, which is summed together, which comes out to 1482. Now, how will you get the vehicle damage factor for this category of vehicle? You sum up what is the damaging effect due to the front single axle and the tandem axle. You get the total damaging effect divided by 273 vehicles were surveyed in this. So, divided by the 273 will give you the truck factor for this truck as 6.253. Now, moving on to the next truck category, which is a 4-axle truck. As I said, you have like 3 categories of axles, which is named as 4 axles. Okay. So, first of all, you have a data for the single axle single wheel, then you have a data for the single axle dual wheel, then tandem axle. So, equivalency factor can be obtained for the first one using a standard axle load of 65 kilonewton, the second one with a standard axle load of 80 kilonewton, and the third, which is the tandem axle, third and fourth put together here. Okay, so the third with a standard load of 148 kilonewton. So, likewise, you see how the data is, the data is, I hope this is visible to you. The data is given here, and let me just zoom it. So, from the data, it is divided into, so all the front wheels, the first wheels having a standard load of 65, and then the middle wheels, which is having a standard load of 80 kilonewton, and then the last tandem axle loads, which is having a standard load of 148 kilonewton, and then the damaging effects for each one of them are calculated as before, and the total damaging effect is computed, which comes to 609, and 81 vehicles were there in this category. So, 609 divided by 81 will give you the vehicle damage factor for this category as 7.528. Now, moving to the next category, which is the 5-axle truck. So, this is the 5-axle truck. You had like 18 5-axle trucks were there in this group. So, 18 trucks. For all the 18 trucks, the rare one, that is the truck axles which I named as 345, is essentially a tridem axle. So, let us see how the data was collected for the tridem axles. For the tridem axle, you have like 3 axles, right? For each axle, 1 wheel is measured. So, this is wheel number 1, wheel number 2 on the second axle, and wheel number 3 on the third axle. Now, each one of them will be multiplied with 2 to get the axle load on the first one, axle load on the second, and the axle load on the third, add together to get the total tridem axle load, which is 380 kilonewton for the first vehicle, and likewise for all the 18 vehicles. So, here also this is divided, there are 5 axles, so this is there are 3 axle groups. So, they are divided into 3 groups here. So, there are like 18 front axle, which is single axle single wheel, then middle axles, which are single axle dual wheel, and the last one, which is the tridem axle, wherein the equivalency factor is computed as axle load divided by 224/4, because for tridem axle the standard load is taken as 224, right? So, likewise, all the damaging effects are summed together and divide by the number of vehicles. You have got for the tridem axle trucks that are considered, you have the vehicle damage, the truck factor as 8.70. So, for the 2-axle trucks, 3-axle trucks, 4 axles and the 5-axle trucks, the naming, don't get confused with the naming. So, that is for convenience only, I have written it like that. So, for all the 4 truck categories, we have determined the truck factors separately. Now, let us see how the equivalent standard axle load is computed. So, let us assume that this is a 4-lane carriageway, single carriageway, so that you can take a lane distribution factor of 0.4. So, you see here they have taken a lane distribution for 0.4, and let us say you have assuming a design period of 15 years. years. Okay. Now the base year traffic data, the annual average daily traffic is computed for all the 4 classes of vehicles, say the 2-axle or the buses or LCVs come under that, which has a per day number of 1859, and the 3-axle trucks have like 2894, the 4-axle vehicles has 782 is the base year traffic data, and 169 is the last category of vehicles. This is the base year data. Okay. Now the truck factors that you have measured for all the 4 categories are here, which is 2.6, 6.2, 7.5 and 8.7 respectively, which is written here. And so multiplying these two, that is the base year traffic with the truck factor, the corresponding truck factor, you can find what is the equivalent standard axle for each of these category per day. Okay. So this is per day, you can just convert it and see how that easel will come, and then you are assumed a growth rate differently for different vehicles. So this information could be available, or for just for the sake of understanding, I have taken different growth rates here. Say the first type of vehicle has a growth rate of 10%, the next is 8, the next is 6, and the last one is 5%. So how will you convert it to the cumulative standard axles for 15 years? You can use the equation as 365 into the growth factor, which is 1 plus r raised to n minus 1 by r into the easel that you have already calculated per day. Okay, because you have already multiplied by the traffic with the truck factor. So you have converted into easels. Then you can use the lane distribution factor. Okay, so this is how that you will compute. So you have the easel multiplied by the lane distribution factor with the growth factor into 365 will give you the cumulative standard axle in 15 years time. Now divided with 10 raised to 6, you can express it in terms of million standard axles. So what you see here is 22.8 million is from the first category of vehicle, 71 from the second category, 20 from the third and 4 from the fourth category of trucks, so that the total equivalent standard axle loads or the design traffic, as you say, is 190 easels. So this is how we can use this template to input the data and calculate the truck factors for each of these categories. And the advantage you have you might have noticed here is that you can, for each of the categories, you can have a different growth rate that can be considered, and then the total easels for the design can be calculated. So this is how we can use this template. Thank you. Okay. Now, let me see a slightly simplified or a different approach wherein you can get this truck factor method. So, what we have seen is that from the axle load data, you have grouped these axle loads into different load groups or different bins. You have put it into different bins of 10 kilonewton or a 20 kilonewton groups, and the mid value of that is taken as the average load value for that particular group. Okay. Now this could be erroneous if the load axle load data is not uniformly distributed in that bin, or if it is skewed in one direction, there could be some error associated with it. So what you can do is that rather than dividing it into different axle putting in different bins, you can just compute what is the equivalent standard axles for all the axles directly by taking the equivalency factor for each one of them. So let's see how that is computed. So this is a different approach in which you can still estimate the truck factor. So we see here is that you have the 2-axle vehicles. So in the 2-axle vehicles, you have the front axle load as well as the rear axle load. The first two columns, or the second and third column here, gives a wheel load. So multiplied with 2, which will give you the axle load. So you can see here this column D gives you the front axle load, and column E here gives the rear axle load of that 2-axle truck that we have discussed. And what is done is that the front axle, that this is a single axle single wheel load. So its standard axle load is 65 kilonewton, and the equivalency factor is the load divided by 65 raised to 4. So for each one of these trucks, so this is truck number 1, each one of these truck, you find what is the equivalency factor for the front axle as well as the equivalency factor for the rear axle. For the rear axle here, It is a single axle dual. So, the equivalency factor is load divided by 80 raised to 4. So, there is no mid value that is considered. You are straight away taking what is the load of that axle and then finding its equivalency factor. Then multiply the front axle with its equivalency factor and add it to the rear axle and its equivalency factor. So, that will give you the total equivalent number of standard axles of the truck number 1. Okay. Likewise, you can for all the 200 and no, how many were there? 208. Okay, so for all the 218 trucks, what you have done is that you have simply calculated the equivalent single axle loads rather than grouping them into any bins. Okay, so you got, then take the average of all this total equivalent standard axle loads, you will get the truck factor for that category. So this has come out as 2.8978. So this is for the first category of vehicle. Now similarly for the second category of vehicles, you see that this was the 3-axle truck. So equivalency factor for the front axle and the rear axle was a tandem axle. For the tandem axle, you find the equivalency factor, and for each one of the trucks, you find what is the total equivalent standard axles, or you can in a way say that this is a truck factor for each one of the trucks, right? Because you have converted into its equivalent standard axles. So it has essentially become the truck factor for the truck number 1, truck factor for the truck number 2, and so on. So average it out so that you get an average truck factor for this category. So as you see here, it comes out as 6.58. Now similarly for the 4-axle truck, so the one with the front axle, middle axle and the rear axle, you see here the average truck factor comes out to be 8.31, and for the 5-axle it came out as 8.93. Then the rest of the computations are similar. You see that the base data is given, you have the truck factors, then easels you get it as the truck factor multiplied by the base traffic, then apply the growth rate and the lane distribution factors and growth factor for 15 years, you get the total equivalent standard axles. You see that it is 127. What we have observed is that if you apply the truck factor, okay, so you have got the design traffic as 127 million standard axles, but what we have observed from the method 1, wherein it is divided into different load groups, is that the design traffic is 119 MSA only. So there could be slight difference. So you can see what was the problem associated with that, because if you put it in different bin groups, some of the traffic may get overestimated or some traffic may get underestimated. So that is the problem when you consider divide it into different various load groups. So these are the two approaches by which you can calculate the truck factor for each truck category and arrive at the cumulative number of standard axles for the design. We will see how the vehicle damage factor is calculated from the axle load data and how the equivalent single axle loads or the design traffic is estimated. Okay. So this is the same data that we have used for computing the truck factor or computing the easels based on the truck factor method. So the same data. The data is presented in this first Excel sheet, as you can see here. As we have already seen, there were like 4 classes of vehicles which were named as 2-axle vehicle, 3-axle vehicle, 4-axle vehicle and 5-axle vehicle for convenience. So this is the data for what is done is that you have like 4 classes of vehicles. You first of all compile all the single axle single wheel loads together. So from all the 4 categories, you will take out this. See, this is a single axle single wheel that will be put together, and you determine what is the equivalent standard axle loads from that category of axle. So you see here, the first, the second sheet here is for the single axle single wheel. So I'll just keep it as such and show you. So this was the first category of truck which has the front wheel data, and that is put together here. Okay, and this is the second class of truck which has the front wheel which is a similar axle. So that data is given here, and the third truck with the front axle, the data is given, and the fourth truck with the front axle. So from all the 4 trucks, the identical axle categories are put together. Again, I have not put it as a single table. For convenience, we have put it in 4 tables itself. So let me zoom it out for you. So this is from the 2-axle vehicle. You had the front axles, which, as we do it for the truck factor method number 1, you can put it in different class categories. Okay, so you can put it in different class categories, the frequency can be measured, and then we know that for all these classes or for this particular class of truck, the standard load is 65. So axle load divided by 65 raised to 4 is the equivalency factor. So multiply the number of axles with the equivalency factor will give you the total equivalent standard axles. So from the first class of vehicle, you got 70, the second class of vehicles is 224, third class of vehicles is 75, and the fourth class of vehicles it is 19. Okay, so sum it up together, you will get what is the total number of equivalent standard axles from this front axles alone, and the total number of vehicles that you have counted is 550 altogether. Okay, now moving on to the second data computation. What now you will see is the next category of axle. So the next category of axle was your single axle dual wheels. So where was it? In the 3-axle vehicle, there was no single axle dual wheels. So that second category of vehicle, there was no single axle dual wheel. Now coming to the 4-axle vehicles, there was a single axle dual wheel, and on the 5-axle vehicle also there was a single axle dual wheel. So all this single axle dual wheel data are clubbed together. So you see that this is from the first type of vehicle, this is from the second type of vehicle, and this is from the third type of vehicle. All common type of axles with a standard axle load of 80 kilonewton. Now using the same approach, you find the equivalent axle loads, you sum up together. So you get the total equivalent single axle loads due to this axle type. Okay. Now moving on to the tandem axle, you had like 2 vehicle classes where there were tandem axles. You classify, you pull out that data and find the total equivalent standard axles. And now similarly for the tridem axle, we had only one vehicle category where there were tridem axles. So for that you will find what is the so you find what is the damaging effect. So 102 is the total equivalent standard axles from this axles. Now we have seen that you have computed the total equivalent standard axles from the single axle single wheels, all the categories of loads put together, all the categories of vehicles, it comes to 390. Then for the single axle dual wheel, it comes to 624 as you see here. Then for the tandem axles from all the vehicle categories together, you get a damaging or the equivalent standard axles of 1906, and from the tridem axle you get a value of 102. Now let's see how the equivalent single axle loads or the design traffic can be estimated from this. So by calculating the vehicle damage factor. Okay. Now see, this is the total number of equivalent standard axles that we have just now measured or computed for single axle dual, tandem axle and tridem axle. So the total equivalent single axle loads for all the vehicles put together comes to 3023. Now you have like 580 vehicles which are considered in this study. So the total equivalent single axle loads divided by 580 will give you one vehicle damage factor, which is 5.2126 for the all categories of vehicles put together. Now let's use this VDF to find the design traffic. Like in the previous case also, here also let us assume that there is a lane distribution factor of 0.4 and the design period is taken as 15. And the base year traffic, you don't need a categorized traffic volume count, you just need the total vehicle volume count, which is 5704 in this case. And the VDF as we computed is 5.2126. Now, the e-cells per day can be computed as the traffic on the base year multiplied by the VDF. Okay. Now, once you get the e-cells, now it has to be projected to the future. Now the thing is, you can't use different growth rates for the different classes of vehicles. You have to choose only one growth rate for all the vehicles put together. So let us assume that the maximum of 10% is the growth rate, and you apply the growth factor, which is 1 plus r raised to n minus 1 by r. and multiplied with the easel per day into 365 into the lane distribution factor will essentially give you the cumulative number of standard axles for 15 years. Okay. And divided by 10 raised to 6 will give you the value in million standard axles. You see that it is 137.92 MSC or million standard axles. Okay. Now, we've seen that the vehicle classes have different growth factors. Now, if I take a growth factor of 7%, instead of 10, you see that the design traffic comes down to 109. So, it is very important that you choose the very appropriate annual growth rate if you are essentially going for one growth rate for the estimation of the design traffic, as in the case of this VDF method.